This is quite fun, being in front of everyone here. So yeah, my name is Anthony. I'm quite happy here because it's not every day I get to be in a crowd amongst my tribe, other engineers, builders, founders, tech people. So I'm very happy to be here. So for my entire career, I've been obsessed with one thing, which is building systems that don't break. But that's not realistic, right? So the fallback plan is building systems that, when they break, can tell us why they are broken. And doing all of this time, I kind of realized one thing, which is that software monitoring is a solved problem. Skeptical faces. But yeah, I'm joking. I really do not think it's a solved problem. So, I mean, we have dashboards. As an industry, we track a lot of things, metrics, P99s, uptime, all kinds of numbers. And our dashboards are all so green that even a Christmas tree would be jealous. But I'm pretty sure everyone here, or at least the people who have been responsible for managing systems, have experienced something I call the green dashboard paradox. So the green dashboard paradox is that situation where all your dashboards are green, your logs show every request is a 200 OK, everything looks good and shiny. Your alert channels are all empty, silent, quiet. But then your customers are pulling their hair off and on social media ranting about how your platform just is not working. And this is not a theoretical situation for me. It's actually quite personal. So in 2019, I used to work at a multinational here in Germany, a big multinational. And we were doing a sort of a migration from some legacy systems to a more modern system that could handle the traffic and the business needs. So we were very careful. We had all sorts of tests. We had monitoring. We were very confident in what we were doing. And then we deployed. Everything seemed great. The deployment was a success. The endpoints were returning what we expected them to return. Until someone, I think from finance, asked, why is the revenue from certain countries down? And then we just panicked. Right, we were all scrambling, looking through logs, looking through the metrics, but nothing. Everything was green. Everything was no alerts, nothing. It took us hours. Actually, this image is probably what my notification bar looked like at that point, I'm sure. So it took us hours of just comparing, painstakingly and manually comparing payloads to catch the issue, which was one single field that that we did not expect. This was a migration from some PHP system which would treat both of those kind of fields as the same and pass them with no problems. But then with our new strongly typed rewrites, was not able to. So by the time we found, this one single field, this one small issue, we had already lost more than $2 million worth of orders. And so it was quite painful for me since I sort of led that migration. And after that incident, I got a bit obsessed with the question, or questions like, what could we have done different? Why couldn't we catch that issue? Why did not even a single alert go off? Our metric monitors say that the latency was good. The error trackers were pretty empty. No errors, no new errors, no exceptions. The trace explorers showed that all the spans were completing fine. Also, no errors over there. But then our system wasn't down, but then it was not doing what it was supposed to do. So we're detecting noise, but we were not able to detect the meaning within that noise. So that pushed me to this question, how do you catch bugs that you're not able to anticipate? There's a quote that I like very much by Donald Rumsfeld. Donald Rumsfeld was the US Secretary of Defense at the time, or at least 2 times, I think. And he says this quote that there are known knowns, things we know. There are also known unknowns, which are things we do not know. But then there's also unknown unknowns, and that's the things we don't know that we don't know them. And that third group of things are usually the most painful, and they tend to be the most difficult things to react to. When Donald made this quote, he was speaking about war, right? Not the most fun topic, but I actually feel that software engineering and software monitoring, especially in production with live customers, is really no different than war. So I would break down those groups with some examples. So for known knowns, an example could be that at some point your database might go down. And because you know that your database might go down, you're able to anticipate and do something. For example, have fallbacks or have, for example, master-slave replication so that if one goes down, you can fall back to the other. And have different kinds of failovers. Now, for the known unknowns, let's stick into that example. We know the database could go down, but we don't know when it will go down or why it's going to go down. So we create runbooks, and we have an on-call system where there's always someone. So in case one of these kind of things happens, there's someone who can apply those runbooks and react to them pretty quickly. But then there's unknown unknowns, which could be super random. I can't find a good example because that's why they're unknown unknowns, but imagine if your database is running, it's up and fine, it's returning responses, perfectly healthy, but then it's returning a customer phone number in a customer ID field, for example. So it's not doing what it's supposed to do. And maybe you don't anticipate that. I'm just giving some random example. So your system is not down, but it's semantically incorrect. When I describe these kind of problems, I usually get responses from very smart developers trying to offer sort of rebuttals of with points like why didn't you just do blah blah blah? Or why can't you just do X Y Z? And yes, there's always a lot of things you can do. Usually in hindsight, for example, in hindsight, you could have tested all of those cases that could happen. But then the reason why some issues are unknown unknowns is because you just don't anticipate them. But some modern what ifs that maybe could actually help would be, for example, why can't you just send all of your traffic to an LLM? And this is a 2025 answer to most questions these days, because these LLMs are these catch-all, super powerful tools that can do anything. But the simple answer to why you can't do this is it's speed and cost. I mean, you can't try to send every single request that goes in and out of your server to an LLM, but then you would probably bankrupt your company while doing that. And not counting the fact that LLMs take some time. They probably take a second or two to give you a response, and for each request that is coming in and out of your server, that would just take way too long. And For the cost bit, I mean, even the most modest service is doing thousands of requests per week or per day, sometimes even per minute. So imagine how much tokens that would cost. Yeah, OpenAI would probably be very happy. So another option could be, we still want to maybe take advantage of LLMs, but we can't send every single thing to them. So why don't we try to group them or summarize them in a way that it becomes small and we can send to an LLM. And Drain 3 is one of the most popular log clustering algorithms out there. If you've used something like Grafana or Datadog, they have this thing where they can cluster a lot of the logs that are coming in and out of your server and just show you templates, so buckets of logs. Now, so this is really great tool. The main challenge is that it's super great for unstructured text. So it can take random logs like I showed you and create a template out of it. The main challenge is that it's not so good for structured data or structured semantics. It will try its best. It can take, for example, these JSON logs and convert them into some templates. But with the way it works, it's not aware of structure in structured data. So it's very easy that you would lose some of the structure you already have. But then you also lose some semantic meaning. For example, if we get these templates, like what I have there, we lose some of the semantic meaning that maybe 50% or 60% of the requests usually have a status of success, and some other percentage usually has a status of failure. And that ratio, that is part of the semantic meaning that you would want to keep an eye on to catch anomalies in this data. So Drain ends up not being as helpful as we would like when we are looking at structured data. And this is very important because most of the data that goes in and out of our systems tend to be structured. Even our logs these days, the current industry best practice for logs is to produce structured logs, and most of the popular logging libraries are now optimized for structured logs these days. So that becomes a fairly big challenge. So that $2 million incident that I described before, it kind of showed me that there is some blind spots in our tools. And I realized that the only way we could catch a lot of these semantic bugs is if we even have the data to mine for these issues. And that would mean, for example, tracking the actual request and response payloads that are going in and out of our system so we can mine them for anomalies. But then if we're now tracking all of these events and payloads and logs and all of that, it brings in second problem that it's just a lot of data. And most of the existing tools out there, they get very expensive when it's a lot of data, or sometimes even impossible. So they try to encourage you to sample. And the challenge with either you sample or you have very small retention period. I spoke with quite a lot of people who are kind of forced to have like a 3-day retention period, just because it's just too much data. So that kind of pushed me towards building something that's building Monoscope. And so I built it because I just had these different philosophies. One that a good monitoring tool should be open source, because if you're building for developers, you want the developers to play a big role in how it gets shipped. The second thing was that if you're encouraging people to store all of this data so they can mine it for anomalies, then who owns that data? You want people to own their data. And the approach that seemed to make sense was if customers could actually bring their own storage, for example, S3, and then have all of these crazy payloads be stored in industry formats. And in the last few years, especially with the whole AI and data boom, there's been just so much innovation in the data topics, with formats like packets, files, and iceberg, and delta lakes. So you can take these huge terabytes or even petabytes of data, but then when they're stored properly, you end up going from like terabytes to gigabytes, just because they are really optimized for that problem. And we wanted that we felt it was important that people have access, they own it, and they can use whatever tool they like to make sense of this data. So now, we've figured out, like costs, because people own the data, and the data is stored in this very compressed and very optimized formats. That still brings us back to the problem. This data needs to be mined. You have billions of events and logs stored somewhere, and now you have a haystack with so much data, but how do you derive any meaning out of all of that data? I mean, think about it. If you have like billions of successful 200 OK payloads sitting in some data lake somewhere, how do you catch new anomalies in those payloads? So you need a way to summarize this massive structured data into smaller subsets that can be reasoned about. And our search for a solution led us to a very old and I think a very cool data structure, which is the Merkle tree, which basically works based off cryptographic fingerprinting. So this is a very small graphic that I created to try to illustrate. Who here uses Git? Obviously, I'm in the right crowd. So everyone uses Git, and in Git, the Git commit hash represents your entire code base, right? But then when you change even a comma or a full stop within that code base, you end up with a new hash, which shows you that there is some difference. Merkle trees are kind of similar. So a Merkle tree is the same idea, but for raw data. So it's basically a hash of hashes that represent all of the data you're trying to track, such that when any bit of the underlying data changes, the roots at the hash or at the bottom, like in here, also changes, which then points to the fact that something has changed, and then you can walk the Merkle tree to find out exactly from which sections of this data the change has happened. But the main benefit is that in the end, you have a very, very small hash that's like 8 characters that can represent the entire data set. And if you go a step further to track all the other hashes in between, you have this like very, very succinct way of knowing exactly where changes happen from. So how we do this is, so first we take this structured data, which could be like, let's say, a JSON for a HTTP request and response. So you have this huge JSON, and then we walk through it level by level. At each level, maybe first of all, we sort it so it's consistent, because anytime you're doing hashing, consistency is very important to get the same hash at the end of the day. So we walk through it, and then we normalize each of the values. And how we normalize these values is actually very simple, which is by having a heuristic of regexes. And what we're trying to do is we're trying to replace every value within the structured object with a common denominator that represents all versions of that kind of data in that group. A simple example would be replacing every case of a UUID with a neo UUID or a very specific UUID. So now you know that, okay, this place holds a UUID, but you're not necessarily tracking every single one of those UUIDs. Same thing with numbers. You can represent all numbers with like 9. And then if you have a number like 22.33, you end up with 99.99. But that shows you the shape of the number that is being stored, but not necessarily the detail. So now we have a key value pair that is normalized, and we can hash each of these values within a level of the object, and then hash the hashes and then hashes until we have one hash and a list of hashes along the way. So just like that, we've now found a way to go from basically we found a solution to this too much data problem, because we now have a real-time, always available summary of all the data that is passing through our systems. So you go from having you still have the 1 billion events, but you find out that when you summarize it, you have like under 1,000 unique shapes of data that passes through your system. And with the Merkle proof, it means that every time a new shape appears, you have an automated system of knowing that something you haven't seen before has just showed up, and then you can dive in and figure out if that is important or critical. So how does this help with, for example, that $2 million incident that I described in the beginning? So let's give an example. You've built a system that is making a lot of API calls, let's say to Stripe. And then all of a sudden, customers are complaining that payments are failing. But let's say your dashboards are green or something, just that some payments are failing. If you had a continuous Merkle fingerprinting algorithm just running on each of those API calls, in no time, you would get a notification that, oh, we found this new Merkle root hash that we've not seen before. And so now we don't have to search through a billion logs. We just compare that new hash to the closest hash that looks very similar, and then we can very easily get a diff of what is different. So just boom, just like that, you have an incident, but not the generic incidents we're used to. So instead of someone saying, oh, our error rates are high, you get a very detailed message like, oh, from these API calls to Stripe, we've discovered a new fingerprint, and that fingerprint says that the customer UUID field is now null. It was never null in the past. So that becomes a very clear message of what has happened, and is very actionable, without an engineer having to spend days fishing. And we can catch a lot of issues. For example, if you're tracking the rates of each of these hashes over time, you can track patterns like, for example, how often you're getting rate limited, because the fingerprint that represents a rate limit message is increasing or decreasing over time. So let's bring it back to that LLM idea. So the original issue with the LLMs was that it's just too much data to send to an LLM. But now you have a way of taking these huge payloads that we're storing and condensing them into a very fixed and limited number of summaries. Like, for example, under 1,000, even though you have billions of events. And it opens a lot of possibilities. For example, you can send this very small subset of summaries to an LLM and use the LLM for some of the decision making. For example, categorizing, what is going on this event. In the case of a new fingerprint, you can use it to, for example, know if a change that happened is critical, if it's a breaking change, or if it's just a harmless anomaly. So it turns out that LLMs, they are very good at reasoning, and we can use them exactly for that. In practice, what it looks like, a tool like this is that you get alerts with showing you exactly what changed in any APIs or any systems you have, and if it's critical or if it's or harmless. And this model I described works very well for errors as well, and helps you know when there's a unique error or an error you've not seen before. So in summary, the Merkle tree is our summarization engine, or a very good summarization engine for structured data. And when you've gotten this summary, you can leverage LLMs for what they are good at, which is reasoning. And together, we can build systems that can detect the previously undetectable. So yeah, thank you.